And then let's get started. Okay, I'm very pleased to introduce Professor Tongyan from the University of California, San Diego as our seminar speaker. She received her PhD degree from Harvard University in 2012 and joined the University of Chicago, followed by Berkeley for her postdoc. She has joined the UC San Diego as a professor since 2017, right? I guess, yeah.
Mm-hmm.
And she's an expert on BSM phenomenology, especially dark matter physics. Today, she will tell us about the dark matter interactions in low threshold dielectric materials. So please.
Great, thank you for the introduction. I'm glad I could see you all talk about the work I've been doing over the last year or so. And this is all related to direct detection of sub-GeV dark matter. And I'm using the word with dielectrics because that's kind of the approach I'm going to take. But the dielectric materials are just kind of the standard materials being used for direct detection of sub-GeV dark matter, just a typical semiconductor target that's being used, which is the case I'll look at in most detail. So I'll be describing the work we've been doing to understand the dark matter interactions in these direct detection experiments a bit better, particularly dark matter electron scattering and the Migdal effect, depending on how much time I have. So I'll start off with just the kind of big picture of dark matter direct detection, at least in some cartoon way, which is the usual way of presenting it is that we have some gravitational evidence for dark matter from the early universe, rotation curves, CMB. And on a separate dimension, we're doing particle searches, meaning we're searching for the particle interactions of dark matter through indirect detection, collider physics, and direct detection, usually presented by drawing a particular diagram of dark matter interaction with the visible sector. And we want to use these particle searches to determine what this dark matter actually is. And this diagram is really based in the thermal freeze-out story of WIMPs, where you can have this interaction also setting the relic abundance in the early universe. In recent years, the kind of way we think about dark matter searches, I think, has expanded quite a bit. So there's no longer as clean of a separation between, say, gravitational evidence and particle searches. One example is now many people use the CMB to also look for, as a probe of particle interactions of dark matter. One example I've worked on in the past, for instance, is if you have this dark matter annihilation to the standard model, that's indirect detection, which we can look for today, but it also happens in the early universe, could impact the CMB. Gravitational probes could also give other ways to test dark matter interactions. For instance, if there's strong dark matter self interactions, that will impact the clustering. And on the collider side, these have also expanded from the traditional high energy searches, for instance, at the LHC, to a much broader range of high intensity or lower energy searches. Sometimes these go under the name accelerator experiments or high luminosity. As well as searches directly for kind of dark sector particles, not just the dark matter itself, but some other light mediator below the GeV scale. So all of these ideas are really arising in part to the idea that there could be some new physics or dark sector, the GeV scale and below. And so the thing I'm going to be talking about today is in particular what happens for direct detection when we consider dark matter at the GeV scale and below. And that also has really broadened in recent years to go not just from dark matter nucleus scattering, but to include dark matter electron scattering, as well as dark matter scattering to create more general kind of condensed matter excitations. And ideas for how we can exploit those different systems to look for such lower mass dark matter. So that's the broad context of what I'm talking about. And so let's dive into direct detection, the goal of which is to look for this dark matter in our galaxy. So here's the usual cartoon for direct detection of dark matter above a GeV. I have dark matter scattering off of a nucleus, and it'll give rise to a recoiling nucleus that deposits its energy in a few different channels. These are usually heat, phonons, scintillation photons, or charge. And a lot of the experiments looking for dark matter above the GeV scale are focusing on at least detecting two of these channels of the recoiling nucleus, reconstructing that nuclear recoil energy. And that'll generally work, that's working right now for recoil energies of about keV, with these very strong exclusion limits on the dark matter nucleon cross-section above the GeV scale here. But as we see, we have a lot of open parameter space below the GeV scale, and these limits are rapidly becoming much weaker. So on the one hand, there is this experimental reason that if you require two of these detection channels, which is of course important for background rejection, if you require two of them, right now the thresholds are on the order of keV, and that's going to be difficult or it's a challenge to keep lowering that to get to lower mass dark matter. On the more theoretical front, there's also another issue with detecting lower mass dark matter, which is that the energy transfer from the dark matter to the nucleus itself becomes much less efficient. So one way we sometimes phrase this is that there's a kinematic mismatch. If you look at the energy and momentum of the incoming dark matter, the relationship between the energy and momentum is going to be very different than the relationship of the energy and momentum of the nucleus, because the masses of the two particles are very different. So that translates into a maximum recoil energy, which is scaling as dark matter mass squared, rather than as the total dark matter kinetic energy, mv squared. So if we think about this in terms of this kinematic mismatch, and now we're motivated to look for this lower mass dark matter, there are, broadly speaking, two kinds of scattering interactions that are now being considered in the literature. One is dark matter electron scattering. So here's my little cartoon again, dark matter creating an ionized electron. Another one is dark matter phonon scattering. So here, this is my cartoon of a lattice of nuclei in a crystal, for instance. And for low mass dark matter coming in and scattering, what's going to happen is it creates collective excitations or phonons in the lattice rather than a single recoiling nucleus. Both of these kinds of interactions have better kinematic match with MeV scale dark matter. So let me go through the numbers for that. Suppose we're interested in MeV scale dark matter, then we can just use the properties of this dark matter in our galaxy to determine ideal energy and momentum scales that we'd like to transfer. So ideally, we transfer an order 1 amount of the kinetic energy of the dark matter. So for the typical velocity of 10 to the -3 in the galaxy, this would give EV for MeV scale dark matter. And ideally, we would, for a good kinematic match, we would also be transferring an amount of momentum similar to the initial momentum of the dark matter, mv, which would be about keV. And so you can compare that then with different targets and the available energy and momentum of the excitations, or the energy and momentum of the available excitations. So for instance, for electron excitations, the energy scale is being set basically by alpha squared ME or lower, depending on if you go from atomic to solid. So that's going to be of order 1 to 14 EV in a very typical, atomic material or some insulator or a semiconductor. And similarly, the momentum scale is set by alpha ME, the inverse Bohr radius of about 4 keV. Meanwhile, for phonon excitations, if you look at single phonons, the energy scale of a single phonon is below about 0.2 eV, and the momentum is below about keV. So from this, we can gather that electron excitations in conventional materials are going to be quite good targets for dark matter at the MeV scale and above. And phonons are going to be quite good target for at MeV scale and below, given these. So that, of course, is just the kinematic matching, and then you have to go through and now calculate the interactions. But this at least tells us that the kinematics is in the right place to start with. And so I'm not going to say much more about dark matter phonon interactions, but I'll just point you to a recent review worked on with Yoni Khan that describes this kinematic matching and dark matter phonon interactions in much more detail. All right, so let's focus in on dark matter electron scattering, which has become a very big topic for sub-GeV direct detection. As I was just saying, it's one advantage of it is that we can now use the available energy eigenstates of the electrons in the material rather than talking about free particle kinematics. Right? We're never scattering off of free electrons. And as a result, this is why it's so important that we now need to understand the many body physics and the details of these materials, because we need to know the eigenstates and wave functions in this more complicated system. So as a cartoon of the available eigenstates, here's what I mean generally by semiconductors and insulators. So you could look at the electron band structure with the occupied levels. And for an insulator, I just mean something roughly of 10 EV gap for the electrons to be excited. So that would give you sensitivity of dark matter down to 10 MeV. That could be xenon. Other things that have been proposed are like a diamond target or silicon carbide. A semiconductor will have a somewhat lower band gap, typically around EV or a few EV. That's the conventional germanium and silicon semiconductors, which are used, are just, very widely studied and already used in some experiments. And then more of a aside, there's also been studies now of more exotic materials you could consider to lower the band gap. So not exactly metal, but things like superconductors or direct materials, where it can be as low as millieV. So there are already a number of experiments that are showing that they can be sensitive to a single electron excited from the being excited to the conduction band, from the valence band to the conduction band. Just as here's a brief cartoon of how they might work. So there are a number of them that I've listed below. Some of them work according to the cartoon on the left or the diagram on the left. So the idea is the dark matter will come in to excite an electron from this valence band to the conduction band. The electric field drifts the electron. So the electron's drifted here. The hole that's left behind is drifted there. And this is essentially collected at the end and read out in the form of this CCD. Or this is the CCD, I should say. This is read out. So this is a charge readout. That's what we would call charge readout. It's directly reading out this electron. Another operating principle is that the electron comes out and it's also drifting due to some electric field. But the electric field is much higher and it's emitting lots of phonons. And this is a phonon readout. So one measures the phonons instead. And so it's very exciting to see that both of these are now being used, and there are already lots of existing results already. So this is a summary plot showing a bunch of these different experiments. And so for dark matter in the mass range of 1 MeV to 1 GeV, this is the dark matter electron scattering cross-section. We see now that there's already lots of interesting results from various experiments. And these are still in the early stages, and you see they're already getting close to some interesting cosmological benchmarks. There's one here, Friesen, where you can produce a dark matter relic abundance, for instance. Okay, so there's a lot of promising developments, and at the same time now we need to understand the rates in these experiments. So there are many different papers studying like not just semiconductors, but polar materials, superconductors, semi-metals, scintillators, and so on. And the similarity in all of these is that I'll be able to treat them like dielectrics. Or treat them all as dielectrics and try to put all of the complicated many-body physics into one function. And so the goal of my talk today is to describe the dark matter scattering in semiconductors and all these experiments in terms of what's called the dielectric response, and use this to calculate some new effects, including the Migdal effect. All right, so I accidentally hid one slide and I didn't want to show it. And so I'm going to exit out of this very quickly. I apologize because I accidentally deleted a slide that I wanted to show. Which is why I got a little stuck there. All right. Okay, so this was the slide I accidentally deleted. So I was telling you that it's very promising that the experiments exist, but of course the important thing is one important thing in order to interpret the experiments is that we need to have a robust calculation of the dark matter rates in these materials. And that's where it gets more complicated, where you need to know about the many-body system and all its eigenstates. And so this gives a little bit more detail on how this calculation goes. And this was actually the original calculation presented in these early papers. And I'll show that there's some corrections we can now include by treating it as a dielectric. Okay, so to model the dark matter scattering, you need to know the eigenstates, and that's represented by this electron band structure, which is showing the eigenstates as a function of essentially momentum. Not too important what these labels are. This is some momentum label. And so we have dark matter coming in to create a hole in some excitation. So the dark matter can be, so we can describe this in terms of a momentum deposited again in an energy deposition omega. So in order to calculate this, you can make an approximation called the independent particle approximation. And if you do that, then the rate looks kind of like you might expect from just a quantum mechanics approach to this, which is that you'll have some final state wave function, some initial state wave function, and you want to compute the wave function overlap with your particular interaction. So you need to know the details of the wave functions and compute this overlap. And of course, you need to sum over the available states L into the available excitations L prime, subject to momentum conservation. So this is just to illustrate the importance of the many-body effects. As we'll show, in fact, even this approach is missing some that we'll include. All right, so let's do now that we can treat all of these as dielectrics. And what that will allow us to do is kind of package all the details of the band structure and those wave functions into useful in terms of thinking of all these materials and interactions on a more similar footing rather than comparing individual band structures, for instance. And I'll pause here if there are any questions for getting into the main part of the talk. Otherwise, feel free to interrupt throughout.
Actually, I just have a simple question, probably. Like your theory line that you showed on your limits plot. There was some assumptions made, I guess, for that, right? That's a little bit model dependent. Is that true? I mean, is there anything to sort of briefly address about model dependencies of that line?
Yes, that's one particular model. So
Okay.
I would say you can definitely be off that model in some. You can be off that line in some other model. It's not to say you can only be on that line. It's just it's an interesting case because it's one where it's a dark photon model and you just have the dark photon and you produce the relic abundance.
So,
Okay, so it's kind of just a simple.
Sorry. So this is the ultralight mediator, right? That's this in.
Yeah. This is the ultralight mediator limit. Yeah, thank you.
Okay, yeah, that's good. Thanks. I just wanted to clarify.
Yeah, it's one particular case where the dark matter is always out of equilibrium, and it's only being produced from the standard model into the dark matter, and then the dark matter never has any relevant annihilation.
The function f is a form factor.
Yes, yeah, this FDM is the form factor,
Okay.
and this is the one for ultralight mediator. Yeah.
Yes, thank you.
Okay, yeah, if there's anything else, feel free to interrupt. So in this next part of the talk, I want to describe what I mean by thinking of dark matter direct detection in terms of dielectric response. So the approach I'm going to take is I'm going to think of dark matter as coming in and creating some perturbation. So basically some potential here that the electrons see. So you see this potential is basically just a usual potential with mediator mass. So it is assuming a spin independent interaction. And these couplings G chi and GE of the mediator between electrons and dark matter. So instead of thinking of a more particle language, I'll think of it as some external perturbation to a system, a dielectric. And in the presence of this perturbation, the system will have a response function, which of which there are two that I'll discuss. One is the dielectric response, which is the response of the electric fields in the medium. And the other is the susceptibility, which is the response of the electron number density in the medium. So the first one, the dielectric response, is the familiar one from electromagnetism. So if we have just a dielectric material, essentially we'll have some induced electric field, which will screen the total field. Or screen the external field. So the total field will be the external field divided by dielectric constant in the homogeneous case. More generally, I'm going to consider a dielectric function, which depends on both which I can write, I can write in Fourier space in terms of frequency and momentum. So this is just describing the screening of the fields. On the other hand, you can basically show from electromagnetism again that the amount of screening you have has to be related to the amount of induced charge you have. So the picture we have is that when you have apply this external field, you induce some polarization. In other words, you're inducing some charge response in the material. Electrons are moving around. That's described by the susceptibility, and the two have to be related to each other. So that's just E&M, but that basically is what's going to allow us to describe dark matter electron scattering in terms of the dielectric response. So when we have an external probe or perturbation that's coupling to the charged particles, we want to find out what's the energy loss rate into these charged particles. Then we can obtain that just from the imaginary part of this charge response. That's going to give the dissipation in the charge response or energy loss. And that's precisely what we want for calculating dark matter scattering. And so just from this first argument and applying the fact that the charge response is related to the dielectric response, that means the dark matter electron scattering rate has to be proportional to the imaginary part of -1 over the dielectric function. So this function, this imaginary part of -1 over epsilon, is also called the energy loss function. The logic I was just describing does not apply only for dark matter. It applies for any standard model probes as well. If you have some fast electron coming in, or if you have X-ray scattering, all of these things will also lead to energy loss from those probes. They're all described by this ELF energy loss function, and so that's why it appears so often in literature and has a special name. And for my purposes, I'm mainly focusing on this energy loss function above the band gap of the material, such that it's dominated by electron loss into electron excitations. You could also look at it below the band gap, and actually then you get the phonon excitations that I was talking about earlier. Okay, so that's basically it. Of course, there's a lot more details if you want to account for the fact that these targets are periodic medium and so on. But basically, through that logic, you can say that the dark matter cross-section is now proportional to some fiducial dark matter electron scattering cross-section. The mediator form factor that we discussed very briefly, and then this energy loss function.
So can I ask you a question at this time? Mm-hmm. Okay, so this energy loss function, would it, as you said, like if I have a different process, not this scattering, but suppose some dark matter goes to an excited state and a photon gets emitted, inelastic scattering, would I use the same this epsilon, this imaginary part of this thing, and then F would be different? Is that the way one think about that calculation?
Yes, yeah, you could, as long as it's a spin independent coupling to the electrons, you would use the same thing. And yeah, the only thing that changes then is what are the omega and k momentum energy that are allowed for your particular, if it's like inelastic, for instance, process. So yes, yeah.
Thank you.
Yeah, and so as I'll mention, we did release some code that has basically these tabulated functions, so that if someone is interested in kind of someone is interested in a different model of dark matter than the ones we considered, it's not too hard to extract the energy loss function we provide, and use your model, and then that way you can calculate it in the semiconductor without having to go through all the band structure and everything else that that you might think you have to do for a semiconductor. Yeah.
Very nice. Thank you.
Yeah, I'll return to that a little bit later, but yeah, so let me describe now the implications of using this. The first one is that, as I'll show, this allows us to account for screening effects, which weren't considered for semiconductor calculations before. And another implication or advantage is that it gives a kind of handle on uncertainties in the dark matter electron scattering rate, because now there are many approaches to calculating and measuring this energy loss function. So for instance, you can try to directly experimentally calibrate this. You can try to calculate it, including more and more many body effects. So it gives a handle on, at least on the material side, how well we understand the scattering. Of course, there's still the dark matter halo side that we, there's also uncertainties there, of course. So let me first comment on this screening aspect. So to do that, let me just consider a little bit more detailed vector-mediated scattering. So basically, I have a new vector mediator, which is talking to both dark matter and electrons through this interaction. And we would know how to calculate 2-to-2 scattering in a vacuum. That's just our usual scattering rate or scattering amplitude. But in a medium, this gets modified, and this was recognized in early work, showing that what will happen is that in a medium, the standard model photon will be polarized. That's basically described by the dielectric function itself. So you'll get this in medium polarization of the photon, which is related to the dielectric function. And similarly, you can get a mixing between this mediator and the photon. So the calculation is a little bit more tricky in the medium. And if you include all of these mixing terms and add up all the relevant amplitudes, what you would see is that the scattering looks a lot like the 2-to-2 amplitude of that you would expect, but it's screened by the dielectric function, which again makes a lot of sense from thinking about just this, thinking about this dark matter as an external probe, which will be screened. Okay, so indeed, this effect was recognized that it should be there. And here's how it shows up in the cross-section that I just showed. So this was the cross-section formula that you can derive. And if you just rewrite this in terms of imaginary epsilon on top and 1/epsilon squared on the bottom, then the top part is exactly proportional to the form factor I showed, or basically the matrix element squared I showed early on. So this part was the wave function overlap between the initial and final states and summing over the available final initial states. Whereas the bottom part is exactly the screening factor of that scattering amplitude. So it has a fairly simple interpretation in that it is just the 2-to-2 scattering but screened. And as I mentioned, this, although this was known to matter, was not previously included in the signal rates for the semiconductor experiments, and it also wasn't included for all mediators, for instance, scalar mediators. And just to make that more explicit, the formula that I just showed does apply for both vector and scalar mediators. And the reason for that is that both of them in the non-relativistic limit give rise to the leading interactions in the non-relativistic limit are quite similar. In the scalar case, that is just the coupling of the number density of electron with this mediator and number density of dark matter with the mediator. And For vector mediators, it's very similar because in the non-relativistic limit, scattering is dominated basically by Coulomb scattering, effectively, and that's going through the longitudinal component, which is basically the zero component, and that has the same form in the non-relativistic limit. So essentially, they give rise to the same perturbation at leading order, which is why I'm using the same formula for both mediators. Okay, so to summarize this first part, using this energy loss function, we see more clearly that it includes screening effects, whereas not all previous calculations did for all these cases. And now let me move on to describe a little bit how we actually determine this and what it gives some intuition for what this function looks like. As I was saying, one advantage of writing it in this way is now, I can share this function with you and you don't have to worry about all the details of the material. But in addition, on the materials or condensed matter side, there's a lot of work on calculating this function because it is important for energy loss of standard model particles. So there's many different approaches to calculating this, and you can use them at different levels of sophistication, including more and more detailed many-body effects as you like in order to try to understand that theoretical uncertainty. On the experimental side, you can also, in certain regimes, if you don't have a good theory calculation, you can also do some experimental calibration. For instance, optical measurements basically tell us this function in the 0K limit. X-ray scattering can give you this function in a very large momentum, like 5 to 10 keV limit. And fast electron scattering can tell you something about it, kind of an intermediate K is like 1 keV limit. So all this provides an additional handle on our ability to predict these rates. All right, so now let me actually give some intuition for what this looks like. So this is a plot of the energy loss function. There's no scale, but this is a log scale. Let me be clear. Sorry about that. So these colors are the energy loss function in steps of, well, the log of the energy loss function. So here I'm plotting the energy loss function in a very simple model, which is just the degenerate electron gas model. So if you just take a spherical, Fermi surface, electron gas with a given Fermi momentum and plasma frequency, you can directly calculate this analytically, and this is roughly what the energy loss function looks like. So this is energy momentum, and you have to live in this region just because that's where you can, for a spherical Fermi surface, you have to live in this region. But there's a collective excitation also called the plasmon. So that's actually a delta function that appears here. But the region relevant for halo dark matter scattering requires that omega is less than kV, where v is the dark matter velocity, and that will be the region down here. So in some sense, you're not even accessing the optimal energy loss function region because you're down here. Now, if you look at more realistic calculations, it basically takes this simple electron gas model and spreads things out because you're no longer restricted to that spherical Fermi surface. So that's what these look like. The plasmon is still there, but it's now not a delta function. It's kind of broad, so that's this resonance. This middle one is a data-driven approach. So basically, we followed some earlier work that was fitting experimental data on the energy loss function and used it to obtain, construct some more analytic version of it. But it doesn't quite work near the band gap. So it's fitting data in some like limited momentum regime, and then it uses it to construct it everywhere in omega k. And then the last one is we used a code, basically a public code that uses the density functional theory approach, which gives the most accurate one, and it's gives 0 response down here because that's where there's due to the band gap of the semiconductor. So there's about an EV band gap, and that goes away. Okay, so that's roughly what this looks like. And once you use it, now we can calculate the rate. Skip that one. So here the left and right side are different mediator limits. And the solid line is the rate that we obtain using this energy loss function that we calculated. The dashed line is what you would obtain without the screening effects. So basically what was done previously in the literature. And so what you see is that the ratio of the two is of order 3 to 5 in this massless mediator limit. So it does suppress the rate by a non-negligible factor in the silicon and germanium semiconductors that are being used. So in principle, a lot of the limits you see should be shifted by that amount. That's for a massless mediator, where because of the form factor, you're dominated by scattering at low momentum, so the effects are bigger, since the screening will be larger at long wavelengths, and the effects are much more mild for massive mediators, just more of a order 1, at most factor of 2 effect on this side. And you can see how that looks translated into the reach in terms of cross section. So again, the dashed lines are the unscreened results that were obtained previously, and then accounting for screening is the solid ones. Again, for massless, where it's about a factor of 3 everywhere, and massive, where it's a much smaller factor. As kind of an aside, I'll note that we also use this to look at the example of a superconductor or metal. And the reason is that that case is interesting because it does have a very large screening, but you also have very large enhancement if you can go to lower energy. So if you look on the right, you can see that the screening effects are enormous here. But despite that fact, it's still potentially interesting to consider these lower band gap materials because they can extend the sensitivity down here for the massless mediator case. Okay, so here's the summary so far. I've explained why we can think of dark matter scattering in terms and rewrite it in just this simple form in terms of the dielectric response, and how we use this basically to wrap up all the many body physics in one thing, and more practically for semiconductors calculate these screening effects. In this last part of the talk, I'm going to describe how we also use this energy loss function for a few other processes, including the Migdal effect, and briefly I'll talk about the other two. Are there any questions before I move on?
You mentioned something about the halo uncertainties. This may be a question for the end that we can save till then, but is there can you kind of comment on sort of which sort of regime, sort of the halo velocity distribution you're accessing, sort of compared to traditional direct detection experiments, I guess?
Yeah,
Yeah, there's of course there's uncertainties because no one knows what it is, right? Nobody's detected dark matter, but yeah, is there basically just a quick comparison? If you want to answer it towards the end, that's fine too.
Yeah, well, I guess one thing I'll do is I'll go back here, and so that's a good point, and I'll just highlight this region again for halo dark matter scattering. So this is omega less than kV. And basically, if you're talking about V, the velocity being near the tail of the distribution, you can lift this up more, right? This band. And you can get more of this like high response region. But at the same time, you're going to be on the tail of the distribution. So definitely for dark matter electron scattering, you're sensitive to how the tail is described, the velocity distribution. And I don't have any plots in my talk, but the uncertainties from that are order 1. So my opinion is now that including the screening effect, which is, you know, the biggest order 1 effect, now the halo uncertainty will dominate. There's for most materials. For the materials we looked at, I think including the kinds of effects I've talked about and also some other ones I won't get into by other authors, that's basically already at the order 1 level, and then beyond that the halo uncertainties dominate because of this fact that really in order to try to access as much response as possible, you actually want to be on the tail of the distribution.
So like, you know, the best configuration for you would be to have sort of an extended very high energy tail of the distribution, as opposed to like, you know, going, you know, having more particles like in the lower parts of that distribution. You really want like a large extended tail, basically, which could exist, of course, but you know,
yeah,
relative to a standard, you know, Maxwellian model. But
that's right.
Okay.
Yeah, you would get a big enhancement. Actually, there was a paper. I'm gonna forget the specific authors, but there was a paper basically earlier this year that ended up using the same energy loss function, looking at I think it was like cosmic ray upscattered dark matter, if I remember correctly. So a population which can live at high velocity in order to get a little bit of a boost, but it yeah, you get a little bit of a boost from like trying to be near here, but I think even in their model it was a little hard to get enough of the tail to really get all the way kind of up here.
Okay. Yeah, that's good. I just kind of
yeah.
wanted to just get some sense of like where you kind of wanted to live, but that makes sense.
Yeah.
Okay, thanks.
Yeah. And I guess related to that, I was about to get to the part where I want to mention that we provide this energy loss function, at least in a certain energy and momentum regime. And so if someone had a model with higher velocity dark matter particles, you can also test it out using our code. So to summarize, there's not just the dark matter electron scattering, but also we describe the Migdal effect in semiconductors with the same energy loss function. So the idea here is that dark matter will scatter off of the nucleus. The nucleus recoils, and usually you're just looking for how the recoil energy is deposited. But in the Migdal effect, there's an inelastic scattering, and the nucleus recoils, and at the same time, there's an electron being excited. And the way we described it in semiconductors is basically this inelastic process where the nucleus is losing energy, or basically loses energy to an electron at the same time. So it's a 2 to 3 process. And the reason the energy loss function appears again is because now you can think of the nucleus as the perturbation or the probe that leads to an electron excitation. So the probability for this electron to be emitted will again be proportional to the energy loss function. And both of these are going to, for both of these, it's going to be the large momentum transfer part of this energy loss function that's particularly important to understand. You can also use this energy loss function for dark photon mediators. So for instance, talked a little bit about dark matter creating phonons. So if this is the dark photon meteor, you can have dark matter come in and excite a single optical phonon. Again, because it's the dark photon behaves just like an electromagnetic probe, you'll get the energy loss function. It's just that you'll care about it for omega below the electron band gap. Another case which has been well studied actually is bosonic dark matter. And that can be absorbed into electrons and phonons. So that gives you, so you can write that rate also in terms of this energy loss function, again, because this bosonic dark matter now is behaving as a probe. So that's another advantage of having this energy loss function. If you can determine it in all its relevant regimes, and for these processes, you really care about the zero momentum regime. You can determine it in all its relevant regimes, then you can calculate lots of different processes relevant for these experiments. So as I was mentioning, because we wanted to make this public so that it would be useful for anyone who's interested in like different kinds of dark matter models, and just wanted to calculate it in semiconductors, but didn't want to deal with going into the whole band structure calculation. So this is basically just a simple, it's a repository that includes the energy loss functions for a few materials. We're starting to add more, that's ongoing, but right now it definitely has silicon and germanium. And depending on your needs, it has some others, but feel free to get in touch if you're interested in that. And it also codes, it has the existing processes I described here already, but you can modify them if you have other kinds of dark matter models. So yeah, we just want to make it easier to consider the phenomenology of dark matter in these experiments. Since I'm getting close to the end, I think I'll just comment a little bit about the Migdal effect, and then wrap up. So as I was saying, the Migdal effect can also be described in terms of this, and I want to say a little bit more about that because it is a way of thinking about the Migdal effect, which is different from the atomic Migdal effect. So to go back, the motivation or the kind of appeal of the Migdal effect comes from the fact that it's giving this extra electron when you have the scattering. So when we have this low energy nuclear recoil, those were the three channels I mentioned at the beginning for how the nucleus could be detected. But for sub-GeV nuclear recoils, it's very unknown, but it's kind of thought that the charge and the light are, the amount of charge or light being produced is rapidly becomes very small below GeV, although that's still uncertain. So a number of experiments trying to detect low energy nuclear recoils are basically relying on just the heat signal and lowering the heat threshold. And there's a lot of progress already getting to very interesting EV scale thresholds. So that's one way forward towards detecting these low energy recoils. Another approach at the same time is to say, right, we don't have charge or light very often, but on the rare occasions we do, then that could bring it above our current thresholds, and we should search for those rare processes. And indeed, there's a couple of rare inelastic processes that have been identified. One is just bremsstrahlung. So when you scatter off the nucleus, it can radiate off a photon. And another is the Migdal effect, which is kind of the close analog, but instead of radiating the photon, you just excite an electron. And so by having this electron, you can now get a signal from this nuclear recoil, even when the nuclear recoil energy itself is so small that you're not really seeing it. So you just look for the electron. And this was applied, introduced in recent years and applied for atomic targets. So for instance, xenon. And the calculation or the picture of how it worked there went like this. So dark matter comes in and it's going to kick the nucleus. And these bands, these shaded regions are representing the electron wave functions. When the nucleus gets kicked, after it gets kicked, if this is happening quickly in some sense, if it happens quickly, then the electron wave functions are still unperturbed in this cartoon, and they haven't caught up yet. And what that effectively means is if you were to look at the wave functions about the moving nucleus, the original wave function has an overlap with the excited electron about the moving nucleus. So that's basically this probability that I've written here. So you take the electron wave functions about the moving nucleus by boosting the, you take the wave function overlap with the excited state to find the transition probability. So this will give you a very small probability for this shake-off electron, but you might want to take that penalty right now because it allows you to actually detect the signal. So one question or potential issue with this way of thinking is that it doesn't clearly apply when you go to a semiconductor. Semiconductor is a lattice of nuclei, and the electrons are not just localized around one nucleus, right? They're delocalized wave functions. And so we needed another way of thinking about it. And so the idea we had was to treat it more like the bremsstrahlung calculation, so that when you calculate this, you're basically calculating just a simple or just a straightforward 2 to 3 process, with the caveat of lots of less simple materials, less simple details, because you're in a periodic material. But it's basically very similar to bremsstrahlung, but with this additional Coulomb interaction that emits the electron. And so if you do that calculation, so what we found was that you could write the dark matter scattering rate in terms of the usual dark matter nucleus scattering, some sort of form factor accounting for the fact that we have a crystal with, we have all these nuclei in a crystal, and they're in, basically you can think of it as harmonic potentials. And then the last part is the probability to excite an electron, and there now you see this energy loss function appearing for the reason that I mentioned, because we can think of now the nucleus as a probe leading to excitations. All right, so if we put that all together and now we use those same calculations to calculate the Migdal effect, you actually find that the rate can be much higher in semiconductors than in atomic targets. So this is the rate as a function of energy for semiconductors, and this is the one for atomic targets. And it's much higher because there's a much lower gap for excitations, essentially. And so this is the last plot showing that if you use this Migdal effect, then you can be sensitive to sub-GeV nuclear recoils, for instance, down here, potentially below the mass sensitivity for elastic nuclear recoils, depending on the relative thresholds. Okay, and this is with the 1 kilogram year germanium and silicon, and actually recasting an existing sensei result gives you this limit up here. All right, so I've gotten to my last slide. The big summary is that the work we've been doing the past year or so is to describe a bunch of different dark matter direct detection processes in terms of one thing called the energy loss function. That's determined by the dielectric function, and it's useful because it's putting a lot of details of the materials all in one function, which we can describe more intuitively in terms of a dielectric response. And furthermore, there's lots of kind of standard ways to get at this, and therefore better understand the rates in our detectors. And lastly, I'll mention again that we did make this, we made this public. So if you're interested in other kinds of dark matter models, I encourage you to use it and feel free to get in touch. But that's it. And thank you. Take any questions.
Oh, thank you so much. So time to ask question for Tongyan.
Hi, I had one question. So for your GitHub module Dark Elf, you mentioned it's modular. Does that mean that if we wanted to just use it as a plug and play tool with some other model, we could use it to extract the energy loss functions and then use a separate code to calculate some analysis that we want to do?
Yeah, I'm not even sure why I said modular, to be honest.
Okay.
But yes, the answer is yes, you can use it in that way. I guess one modular aspect is like there's a piece of it which is just giving you the energy loss function, so you can ignore our like calculations of dark matter scattering in the particular models we considered, or you can take we included the kind of standard model, the most commonly studied models like the dark photon mediators, so you could just modify those if you have a variation on those
Okay,
models as
perfect.
well.
Perfect.
Yeah, and I guess a third thing, oh sorry.
No, go ahead.
Well, a third thing that makes it modular, which I didn't really discuss, is that it's easy to add in a new material. If you decided you were interested in another material and you or somebody else calculated the energy loss function, it's just like adding a folder there, and then you can.
Oh, okay. We need to know like the band structure and things like that.
Yeah.
Okay. And then one last question: is this energy loss function in relativistic or non-relativistic? So if I wanted it to use it with some other kind of, not just high velocity dark matter, but in the more relativistic regime, would I be safe to use it?
You would be safe to use it depending on what omega and k are preferred for your model. So we calculate it and provide it in a particular limit, which is like energies from 1 to 100 EV, and momentum, it's valid up to 10 keV or 20 keV. But if you're depending on the kinematics of what you're studying, if you need it at higher energy or higher momentum, there you might be better off using kind of an atomic approach, actually, because then you're kind of at scales where the semiconductor details are less important.
That
so
makes
you
sense.
have to be you just have to be careful where you're sensitive to. But
it looks like it falls off pretty rapidly outside of that range anyway. Is that correct?
That's it does fall off, but if it depends, it again depends on your threshold and your there are cases where the high momentum regime is important. For example, for like pretty heavy dark matter and high thresholds, then what we provide might not be sufficient.
Okay, cool. Thank you.
So other questions? So I actually have a very fundamental question. I understand if you use the dielectric materials for the dark matter detection, you have to consider this, the effect, etc. But as yours, the briefly mentioned in the talk, so you could use the like effectively like a free electron, for example, in the superconductor dark matter detector. So what would be the sort of the advantage of using the dielectric the material in the dark matter detection?
So I think what I'd say is that if you want to calculate things accurately, then you should use the full dielectric response. For certain materials, it's true that the free electron will give a approximation, actually a pretty decent approximation. So maybe if I go back here. So indeed, actually, if you look kind of in this region in the middle, they all look pretty similar, including the free electron model. But if you want to calculate it accurately, then certainly you need the full results. And in some materials, then it might be worse. It might be worse than this case. Actually, this case looks reasonable, but I don't know if on other materials the disagreement might be larger.
Okay, so I see. Okay, so other questions? Okay, so if not, let's thank the Tongyan again. Yeah, it was very nice talk. And also, if you have the further questions for her, so you can directly contact her, or you can just the email me. Then I'll let you know her contact information. Okay, so Tongyan, thank you so much.
Thank you. Yeah.
Thank you. Nice talk.
Thanks. Good to see you. Thank you for the questions.
Okay, so let me stop.